Okay, so this chapter is correlation and regression. There are two different sections we're going to cover in this chapter. The first section is correlation, and then second one is regression. The key concept in this first section, correlation, is uh, whenever we have given data as two different samples, we try to find out, either they are related or not by finding the linear correlation coefficient R. And we only consider the linear relationship. There might be some other type of relationship we do not consider here. Okay, and then whenever we plot the data, that data, the graph or the scatter plot should be look like a straight line. Then finally we discuss a method for conducting a formal hypothesis test that can be used to decide whether there is a linear correlation between all population value or the two variable. So the summary of the key concept is, we try to look at the correlation between two samples data by trying to find either they are linearly correlated or not. So I'm going to show you some examples here, the examples of the data where they are linearly correlated or not. So let's go to example. Okay, before the example, first of all, let's try to summarize. Correlation exists between two variables whenever there is a relation between those two variables. A linear correlation means the straight line relation between those two sample data. Whenever we try to plot the data using the scatter plot, linear correlation. So this is one of the example. As you can see here, these are the data between two variables x and y, and when we plot the scatter plot, we see that the data is growing. It's going up. As x grows, the y is growing. So x versus y, if we try to approximate this data, then we can see that there is a linear straight line pattern between them. So distinct straight line or linear pattern. We see that there is a positive linear correlation between x and y in this particular example. Here you can see that positive correlation R equal 0.859. That tells us that between these two sample data there is a positive correlation because the value of R is 0.859, and there is, we can see the straight line pattern between the datas. Positive linear correlation between x and y. Here is another example. Here the data, as you can see here, it's going down. As x goes up, the y is going down, and there is a R value which is negative 0.97. And here is the third example. The data is scattered everywhere, so we don't see the distinct pattern. The value of R is 0.074, which is very, very small. So it suggests that there is no correlation between x and y. We don't see any linear correlation here. If we the value of R is close to 1, then that's a linear correlation. This is another example. Here we see the pattern, but it's not actually the linear. The value of R is 0.33, distinct pattern, but no linear. So these are the four examples we discuss. The linear, and then no pattern, and then non-linear pattern. So we use the linear correlation coefficient R. So let's define one more time. The linear correlation coefficient R measures the strength of the linear correlation between the pair of quantitative x values and y value. So these are the examples. The linear correlation coefficient is sometimes referred to as the Pearson product moment correlation coefficient, which was introduced by Karl Pearson. Okay, so our objective in this section is to determine whether there is a linear correlation or not. These are the notation we're going to use. N stands for number of pairs of sample data. Sigma denotes the addition of the item indicated. This is how we write it down. Sigma x is sum of all the x values, and then sigma x square indicates that each x value should be square and then those square added. So there is a difference between sigma x square and then square of the sigma x. As you can see here, there are two different things. One is square first and add, another one is add first and square. So these are the two difference. So there is a sigma x times y indicate that each x value should first be multiplied by its corresponding y value, and then after that we have to add. R stands for the linear correlation coefficient and for the sample, and rho stands for the linear correlation coefficient for the population. So that's the difference, sample versus population. There are some requirements while calculating and interpreting the linear correlation coefficient. And number one, so the sample of the pure data x comma y should be simple random sample. So there are two different type of data we are collecting, and one data we assume that is x, and another data we assume that is y from the sample data, and that should be simple random sample. And then quantitative data, so that's data should be from simple random sample, and then quantitative data. So whenever we try to plot those value, visual examination of the scatter plot must confirm that the points approximate a straight line pattern. So whenever we plot the data, that should be straight line pattern, as we looked at a couple of examples before. Okay, if we go back and then look at the examples, we show that there are like these two, first two are straight line pattern. As you can see, one is growing, another one is going down. So the third one is because the result can be strongly affected by the presence of outliers. If there are any outlier, that must be removed. Okay, so that's our third requirement. Requirement 2 and 3 above are simplified attempts at checking this former requirement. The pairs of x comma y data must have a bivariate normal distribution. So whenever we calculate and interpret the linear correlation coefficient, these are the three requirements should be satisfied. And then we're going to whenever we try to solve problem, these are the requirement we should satisfy. So there are two formula we can use to calculate the value of r. So this is the first formula. So n times sigma x times y minus sigma x times sigma y. So it is very complicated looking formula, but do not worry, we are going to use StatCrunch to calculate this formula. There is another form of the very same formula by using the g-score. We denote g of x denotes the g-score for an individual data, and g of y denotes the g-score for the individual data y. So both of them calculates the linear correlation coefficient, but we're going to use technology like StatCrunch. And for the rounding, after finding the value of r, round it to the up to 3 decimal places, and eventually like before we have to compare. We can use the p-value test or the critical value method, and then if we have the p-value, compare that value with the alpha. If p-value is less or equal to alpha, that supports the claim. If p-value is greater than alpha, then that does not support the claim. If we are using the critical value, then you compare the critical value with the correlation coefficient. Absolute value of r is greater than critical value, concludes that there is a sufficient evidence to support the claim. And if it's less than critical value, then conclude that there is not sufficient evidence to support the claim. So p-value and the critical value, these are the two methods we can use while finding the correlation supporting the claim or not. So some of the properties for linear correlation coefficient: one is always the linear correlation coefficient should be in between -1 to +1, including -1 and +1. They cannot be more than 1, or it cannot be more than 1 or less than -1. If all values of either variable are converted to a different scale, the value of r does not change, and then the value of r is not affected by the choice of x or y. You can exchange which one you would like to choose as x and which one you would like to choose as y. And r measures that number r measures the strength of a linear relationship. It is not designed to measure the strength of a relationship that is not linear. So if it's not linear, then r cannot be used. R is very sensitive to outliers, so sometimes we might get spurious correlation, which is actually spurious correlation will become more common, which is the correlation that does not have an actual association. In real life there is no correlation, but in calculation we might see correlation. That's called spurious correlation. Okay, and that might happen with the big data, or whenever we try to use time series data that have similar trend. So we have to always keep in mind there is the data wise there is a correlation, but actually there is no correlation in real actual situation. So interpreting r, explain variation. The value of r square is the proportion of the variation in y that is explained by the linear relationship between x and y. So that's the one of the interpretation. And then whenever we use this linear correlation relation, always there might be some common error. Example, assuming that correlation implies causality, using the data based on averages, or ignoring the possibility of a non-linear relationship. So you always have to think about this common error involving a correlation. So there might be a relation non-linear, and there is a correlation non-linear relationship, but we don't worry about the non-linear relationship, we just focus on linear. And eventually the conclusion is we would like to do the hypothesis test, and then for that, always the null hypothesis for the correlation would be the population correlation coefficient rho should be 0. That represents no correlation at all. And alternating of that hypothesis is the population correlation coefficient is not equal to 0. So that's the default hypothesis testing. Sometimes it might be greater than 0 or less than 0 based on the situation, and that's also called one-tailed test. And sometimes we have to find the test statistics, and this is the formula we can use. This is the formula we can use to find the value of test statistics t. You can use it manually by using a calculator, or you can also use StatCrunch. So this is the final conclusion. If there is a one-tailed test, it might be rho less than 0 or rho greater than 0. So these are the things you have to. Now we're going to see some examples. Okay, so this is problem number 1. If we find that there is a linear correlation between the concentration of carbon dioxide in our atmosphere and then global temperature, does that indicate that changes in the correlation of the carbon dioxide cause changes in the global temperature? So the answer is no, because even though there is a correlation, linear correlation, it doesn't mean that if you change one variable, it will change other variable as well. Correlation just means based on that sample there is a correlation between them, nothing else. Okay, so the answer is no. Next question, we have given this data. 54 wild bears were anesthetized, and then their weights and chest size were measured and listed in the data set. So here we already have given correlation coefficient, critical value, p-value, everything is given. So we do not calculate these values, but later on we're going to, based on the data, we're going to calculate this value. Okay, so the first question is there sufficient evidence to support the claim? For that we need to do the hypothesis testing. Always for the hypothesis testing, the correlation coefficient for the population is always equal to 0, and then alternating is not equal to 0. So these are the default choices. And then for finding the value of r, it's already given, which is 0.96. If you round it to the 3 decimal places, it would be 5. And then finally our value of r, there are two values of r, critical value of r, they are plus minus 0.268 if you round to the 3 decimal place. And then is there sufficient evidence to support the claim? If the absolute value of r, which is in this case 0.9648, if it's greater than the critical value, then the answer is yes. Yes, because the absolute value of the test statistics, which is 965 exceed the critical value, there is a evidence to support the claim. And you can find that information in your where is that, let me, okay, by using here. So if the absolute value of the critical number is greater than critical value, this is the conclusion. Less than critical value, this is the conclusion. So now, when measuring an anesthetized bear, is it easier to measure the chest size than weight? Of course, that is right, because to measure the weight you have to use weighting tools, and the answer is yes. It is easier to measure a chest size than a weight, because measuring weight would require lifting the bear onto the scale. The chest size could not be used to predict. Okay, here is the thing. We see that there is a strong correlation between the chest size and the weight. So we can use that correlation to predict the weight. So the answer should be yes, it is easier. The chest size could not. No, chest size could be used to predict the weight because there is a linear correlation. So that's our final answer. This problem, we have given data, and then we can use scatter plot. We can use StatCrunch to answer this question. The data list between actress and actor, ages of acting award winners matched by the years. So they are not from the same movie, but they are from the same year in which the award year won. Construct a scatter plot. So we have to graph it, find the value of the linear correlation coefficient R, and find the p-value of R. Determine whether there is a sufficient evidence to support the claim of linear correlation between the two variables. So just click that here. There are two different ways you can go. One, you can use your calculator, and you can use your formula, those formula for finding the value of R, like this complicated looking formula, using your calculator manually, or you can use the StatCrunch. I'm going to use the StatCrunch here. So I'm going to open this data using the StatCrunch. And now to answer all the question, you can just go here, stat and regression, simple linear, and then choose your X variable as a best actress and then Y variable as a best actor. So remember, you go to data and then regression. What is that? Stat and then regression, and then simple linear, because it's a linear relation we would like to find, and rest it's trivial, and just compute. And then when you do that, it gives you all the information you are looking for. The first one you are looking for is R, correlation coefficient, which is 0.288. So this is what we are looking for. But before that, we also have to plot the data, plot the graph. So we also need graph plotting here. So let's do that. How do we graph? Go to graph and go to scatter plot, and choose X variable as the best actress and then Y variable as the best actor. And if you hit the compute, that will give you the scatter plot. Compare your plot and then just choose the right one. As you can see here, the right one would be, where is that? So one is here, first one, and then okay, just compare with the given the options here. And as you can see that there is a first, second, two of them would be, so this looks very similar. See, okay, excellent. Now for finding the value of R, we can just go back and then use the information we calculated from here. The R is correlation coefficient is negative 0.288, negative 0.288. And then the always null hypothesis is equal to 0, and alternating hypothesis is not equal to 0, and that's answer. It's always trivial. The t statistics can be found by using the same table here. Whenever you go to the first table, the slope row, there you can find the t statistics. This is the value they are asking for. You can find this value using your calculator and using your formula, which is this formula, or you can use your StatCrunch here, which is negative 0.95, 2 decimal place, negative 0.95. That's our answer. And for the p-value, it's again already given. P-value is coming from the same row, which is 0.364, 0.364. So now, as you can see here, the p-value is greater than alpha. So whenever you have p-value greater than alpha, so your conclusion should be coming from here. Where is that? No. There is a here. So if p-value is greater than alpha, it does not support the claim. So here in this case, the p-value is greater than alpha, then there is not sufficient evidence to support the claim. Okay. And should we expect that there would be a correlation? Should we expect, because the p-value is greater than this, should we expect there is a correlation? And the answer is no. And there are two different options you have given, and then answer you can give no, because the best actress and best actors typically appear in different movies, so there should not be correlation between their ages. So that is the one of the answer. Let's go to next problem. We have given table, we have given data, and data, there are a huge number of data here. The table below includes the data from taxi rides. The distance are in miles, times in minutes, fares are in dollars, and then tips are in dollars. Is there a sufficient evidence to conclude that there is a linear correlation between the time of the ride and the tip amount? So that's what we would like to find out. So we would like to find out the correlation between the time and then tip. Time and tip. We don't need the rest of the data, but just use StatCrunch and it will take care of itself. We would like to find the scatter plot. So go to the graph, choose scatter plot, and then X variable is time, the Y variable is tip, and just hit compute. It will give you the actual scatter plot, and compare that one with the given. So let me just make it small so we can compare with this. So it looks like this one, the last one, is the closest one. So I'm going to check this answer, and that's a nice answer, nice work. And now for the rest of the information, we are going to do the same thing. We are going to choose stat regression, simple linear regression. X variable is time, the Y variable is tip, and then if we compute, it will give us everything we are looking for. So the correlation coefficient is 0.548, 0.548 if you round it to the 3 decimal place. And then the null hypothesis is always equal to 0. Alternating is not equal to 0. That's the value we have given here. And then the t statistics also, it is already calculated. That's coming from the slope row. Here is the t value, which is 4.54. 4.54. If you round it to the 2 decimal place, 4.54. That's the t value. And then p value is also coming from the same row, the last one, which is less than 0.0000. So that can be rounded to the 0 if you round it to the 3 decimal place. And finally, because p value is less than alpha, alpha is 0.05. If you go to our conclusion, if it's less than alpha, suppose the claim of a linear correlation. So because p value is less than or equal to significance label, there is a sufficient evidence that it supports the claim. Okay. Okay, which of the following is not a requirement in determining whether there is a linear correlation between two variables? If r is greater than 1, this is not required, because r should be in between -1 to +1. So just choose that one.